Hey Calc 2 friends, welcome to Chapter 9, Differential Equations. We're going to start out with 9.1, which is titled Modeling with Differential Equations. I prefer to call it an introduction to differential equations, but either way, let's go. A differential equation is an equation that involves the derivative or derivatives of an unknown function. So, for example, let's suppose our unknown function y be our unknown function. Then an example of a differential equation, we often abbreviate differential equations with DE, is, I don't know, let's say 2y prime minus y equals 7x. So here we're looking for a function y such that 2y prime minus y equals 7x. When we see another variable inside the function, we assume that y is a function of that variable. So y is a function of x. And we're looking for a function where twice its derivative minus itself is equal to 7 times x. A differential equation is considered solved when you find that function, y, or set of functions that satisfy the equation, assuming a solution exists. Not all differential equations have solutions. So let's look at this differential equation, y equals y prime. So that is, we're looking for a function y whose it equals its derivative. One solution is the function y equals e to the x. And we can always check. This is what's great about differential equations. We can check them. If y equals e to the x, then y prime equals e to the x, right? And our differential equation says, does y equal y prime? Well, y is e to the x. Y prime is e to the x. So yep, it in fact solves this equation. But notice something interesting. This is not the only solution to this equation. Note, y equals 13e to the x is also a solution to the differential equation. Y equals y, y equals y prime. Just want to make sure I put it in the right order. All right. So check. If y equals 13e to the x, then y prime is equal to itself. So therefore, y equals y prime, right? As a matter of fact, I could have put any constant there. Y equals c e to the x is a solution to the differential equation y equals y prime for any constant c. So one thing to get used to is when we have multiple letters inside of an equation, it's typically understood that letters at the front of the alphabet represent constants. So A, B, C, D would represent constants, while letters at the end of the alphabet would be our variables. So C is going to be a fixed constant. X and Y are allowed to change. And don't forget, E is that exponential number, 2.7182, blah, 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 right? So as a matter of fact, like I said, y equals c e to the x is a solution to the differential equation, because for y equals c e to the x, the derivative is just c e to the x. So therefore, y equals y prime for any constant c. Right? Here, up here, the constant was 13. Down here, the constant we don't see is 1, but I could put any number up front and it would satisfy the differential equation. This is called a general solution when we have a constant in there that's allowed to vary. When we apply a value to a constant, then this is called a particular solution. And usually when we're given a differential equation, in order to attain the particular solution, we have to be given a little more information. And we'll get to that in a minute. All right, let's look at this differential equation. Right, this is very difficult to solve, but I'm going to give you the solution, and we're going to check that it's in fact a solution. And we'll work on solving differential equations in a little bit. So y is my unknown function. This is called a second order differential equation. The order of a differential equation is the highest derivative. So we have 4x squared times y double prime, so we have a second derivative here. So the second derivative determines the order of the equation. Second order differential equation, the order is determined by the highest derivative in the differential equation. So if we just backpedal a minute to this very first example, this would be a first order differential equation because y equals y prime, we're only taking the first derivative, so it's a first order differential equation. The highest derivative in this example is y double prime, so this is a second order differential equation. I want to show that y equals x to the negative 3/2 is a solution to this differential equation. All right, well, how do we go about this? Well, y is equal to x to the negative 3/2. So that's going to go right in there. We need y prime, so y prime is negative 3/2. X, we subtract 1, negative 5/2. And then we need the second derivative. So y double prime is equal to positive 15/4 x to the negative 7/2. So my differential equation is 4x squared y double prime plus 12x y prime plus 3y equals 0. So we're going to put y in right here. We're going to put y prime in right here. And then we're going to put y double prime in right here and then make sure that it balances out. Right, so we have 4x squared y double prime is 15/4 x to the negative 7/2 plus 12x, and then y prime is negative 3/2 x to the negative 5/2. Whoops, and I'm running out of room. I wrote a little too big. I'll slide this up a little bit. And I'll do plus 3 times y, which is x to the negative 3/2. We want to show that equals 0. Right, so we don't know that this is in fact equal. We're showing it's equal, so we tend to keep everything on the left, and we're going to keep the 0 on the right, and we're going to try to get the left side to turn into 0. So let's look at this first term, 4x squared times 15/4 x to the negative 7/2. We see that the 4's cancel, and our numerical coefficient becomes just 15. Then x squared and x to the 7/2, well, we can add that, put those powers. 2 and 7/2, well, that's 4/2, and negative 7/2 is negative 3/2. And then 12 and negative 3/2 gives me negative 18 as a coefficient, and x x to the 1 power and x to the negative 5/2 gives me x to the negative 3/2. And then we have plus 3 x to the negative 3/2 equals 0. Well, now we have all like terms. We have 15 x to the negative 3/2 minus 18 x to the negative 3/2 plus 3 x to the negative 3/2. So 15 minus 18 plus 3 is 0 x to the negative 3/2 equals 0. 0 equals 0. So there we did. We just showed that therefore y equals x to the negative 3/2. The function y equals x to the negative 3/2 is a solution to the differential equation 4x squared y double prime plus 12x y prime plus 3y equals 0. Right, finding the solution here, I handed you the solution, and we in fact just checked that it was a solution. Finding the solution is a whole other ballgame. There's actually a class and classes dedicated to solving differential equations. So we will learn to solve several types of differential equations, but right now we're just understanding what a differential equation is and checking the solutions. So note y equals x to the negative 1/2 is also a solution to the differential equation. Oops, I'm running out of my page. Here we go. To the differential equation that we were just given, this guy, right? To do, check this. Show, in fact, that this function, y equals x to the negative 1/2, also solves that differential equation. Right, so a couple of examples ago, we talked about that coefficient out front. We saw that we had different solutions with different coefficients out front. So how do we determine if we need to find a value for those coefficients? Well, we'll be giving additional information. A condition or set of conditions that allow us to determine what solutions we're looking for are called initial conditions. They're found by using the values of the function or the values of the derivative at specific points. So a differential equation with an initial condition is called an initial value problem. And I will abbreviate that IVP throughout the notes. So an initial value problem is a differential equation along with an initial condition. So this is an IVP. All right. We know the general solution to the differential equation is, well, we saw that it was y equals c e to the x for any value of c, for c, any number, for any real number c. Right? So now we're going to use this condition using the initial condition y of 0 equals 4. Well, if y equals c e to the x, y with 0 inserted, it's not y times 0, it's y of 0 is c e to the 0, and that must equal 4. Well, e to the 0 is 1, so that's c times 1 equals 4, so c must equal 4. So now we're going to put 4 back in there, and we're going to get what we call the particular solution. So therefore, y equals 4 e to the x is the particular solution to the initial value problem, y equals y prime, with the initial condition y of 0 equals 4. And those would be given to us unless we were creating the model ourselves, but we're not at that point yet. All right, so let's try a slightly more complicated one. Let's look at this differential equation. Let's show the function y of t, which equals 3/4 plus c over t squared, is the general solution to the differential equation 2 times t, y prime, plus 4y equals 3. Now notice this is y of t. If we have parentheses, it's typically telling us that y is a function of t. So my input variable is t, my output variable is y. C is going to be an arbitrary constant. So we're just going to put y right here. So we know that y is equal to, and I'm going to eliminate that t just for simplicity, 3/4 plus c over, t squared. Sorry, I don't know why I slid that down. I'm going to change this. This is what I was thinking, c t to the negative 2. I think it's easier to take derivatives when we change fractions or variables in the denominator to negative powers. Okay, so now y prime is going to be, well, the derivative of 3/4 is 0. Let's bring the negative out front. That's negative 2c t to the negative 3. Right? So now we want to show that it satisfies this equation. So 2t y prime plus 4y equals 3. We're going to put y prime in here, and we're going to put y in here, and let's see what happens. We get 2t times y prime, which is negative 2ct to the negative 3, plus 4 times 3/4 plus ct to the negative 2. And we want to show that equals 3. So we want to do all the math out. This is going to be negative 4c, and then t times t to the negative 3 will be t to the negative 2 if we add the power 1 to negative 3. And then 4 times 4, 3/4 is going to be 3. Right, that times that is just 3. And then 4 times the second term is ct to the negative 2 and equals 3. Well, notice these terms are the same term but opposite in sign, so they cancel. And we get 3 equals 3. So notice I didn't bring anything over from the left side to the right side or anything from the right side to the left side when we're trying to show something is equal, because we really don't know this yet. So you're really only allowed to add and subtract things from both sides when you know that they're equal. That's called the additive property of equality. Same with multiplicative property of equality. So what we do is kind of like imagine a line here, and you don't want to cross the line. So leave everything on the left side and try to get it to look like everything on the right side. So we just showed that this function, y equals 3/4 plus c over t squared, is a solution to this differential equation. I'm going to throw out an initial condition. We're going to take the same differential equation, but we're going to add this condition that y of 1 is equal to -4. So it says find the solution to the initial value problem, the particular solution, when we find that value of c. So we know the general solution to the differential equation 2ty prime plus 4y equals 3 is, well, we already knew it was y equals 3/4 plus c over t squared. So let's add the initial condition. Y of 1, well, when we put 1 in, we get 3/4 plus c over 1 squared, and that has to equal -4, because when we put 1 in for the input variable, the output is -4. So 3/4 plus c equals -4. So c is -4 minus 3/4. Now we want to use exact values, so you could find this on your calculator, and you do get a decimal number. I'm missing -4 minus 3/4. Decimal answer is -4.75, but you're only allowed to use decimal answers if they are exact values. I like to use my fractional values. We started with fractions. I'm going to end with fractions. This is -19/4. So therefore, we say the particular solution to the given IVP, initial value problem, is, well, y is equal to 3/4 plus c, which is -19/4, all over t squared. But we do not leave fractions and fractions, especially at this level in Calculus 2. So we're going to just rewrite this as y equals 3/4, multiply the top and the bottom by 4, and I'm going to get -19/4t squared. So that would be the solution, the particular solution when we add this initial condition. All right, so have fun with those. Look at your PowerPoint lectures, get some idea on how these models are created and how the solutions are found. And we will go through the next couple sections learning how to solve a couple of types of differential equations.